So this is the experiments in the photoelectric effect you'll see in all your textbooks in introduction to modern physics. There's an evacuated chamber, there's a cathode and an anode, and there's light. It's monochromatic, so it's only one frequency. And they put a potential across it so that the electric field pushes back against the cathode. So when there's charge that comes out in response to the light, which goes in all directions, it has to go against that electric field. The electric field force goes the other way, and so they adjust the voltage. Not sure how to draw this. I'm just going to draw a line, like an arrow through it. You adjust the voltage to control this electric field so that you just see at what point will you stop the charges from reaching the other end. What voltage do you adjust to turn off photoelectric effect? And from that, you're able to write down the equation. So I'm not sure if I can do it because I'm out of practice. So there's it's electron volts of kinetic energy. And so we know the volts, and we know the charge, and the equation is supposed to be electron volts equals Planck's constant times frequency. So we know the frequency of what's coming in. They take the charge from another experiment, this charge value, 1.6 times 10 to the minus 19th coulombs, that thing. Voltage would measure, the frequency would measure. So yeah, we're able to get the volts, and then we're able to see. Let me draw in the kinetic energy. I think that's how it's done. The mass comes from another equation, another experiment also. That's part of the problem. The constants that are used in the understanding of experiments, some of the constants will come from other experiments. And so you have to sort out, well, what assumptions were done with that? Voltage. Oh yeah, the velocity. Mass. I could just draw it up here. All right, I'm pretty clumsy about how to derive the photoelectric effect from experiment. They get the voltage. Why do they put in H? Oh yeah, but you'll do it at different frequencies. You change the frequency, you'll put together some graph of frequency versus voltage. You'll see linear relationship. Now, the very first hint of this relationship between electromagnetic frequency and stopping potential. That was done by Lenard. So and that was the important step. He pretty much had the idea of what was going on with the photoelectric effect. But then it was Einstein who introduced Planck's constant as the constant of proportionality in this linear relationship. So it wasn't that hard, if you ask me, to go from Lenard to then Einstein's 1905 particle interpretation of the photoelectric effect. So they model it as a whole electron particle that's going out that way. So the derivation of the photoelectric effect is really using the particle model on this experiment. So how do you reconcile this where what Einstein did was say, oh yeah, it equals the kinetic energy of the electrons. I'm going to put back the mass times the velocity squared. So if you look at Einstein's original paper, after he understood that you're supposed to use Planck's constant, he spent like 10 pages to justify using Planck's constant, and then just wrote down this equation, this part of it. By applying the particle model to this experiment. Now, I do not call that much of a derivation, but what I did is connected this equation to another just as famous equation, which is the de Broglie equation. And the de Broglie equation is Planck's constant is equal to mass times velocity, which is the momentum, times the wavelength of. It's been a long argument. What is the wavelength of? You can see the wavelength in experiments. You can see it in charge diffraction experiments. So you can do it. You can do another experiment to get this equation in charge diffraction. You'll use Bragg diffraction, which is wavelength is equal to, let me try to say what all that is. So in charge diffraction, of charge coming in and have layers. You have to do it with waves. This is a wave-only equation. There's the Bragg equation. And from the angles, you're able to determine, well, it all fits into here. Here's the D, distance between layers. Other people will use layers of atoms. They'll do that. You see that in books.
Mm-hmm.
I just use layers of charge, and I'll model them as standing waves of charge. And that gets sorted out later as to what it is, but it's layers in a solid usually. And so we know D, we know the angle, therefore you can get the wavelength. So you can find the wavelength experimentally. So we got that. Then the velocity, you can get the velocity. This is going to be charge. I'm just going to put E for charge. It looks like a particle, but be warned, it's not always a particle when electrons get diffracted. But we know the velocity from an electron gun, similar to what I drew before, where there was an accelerating, well, in this case it'll be an accelerating potential. So we'll know we'll be able to use this equation. From EV equals mv squared. So from the voltage and knowing the mass, see, the mass of the electron came from another experiment. I'm going to get to that also. But it's a matter of putting together, hard to explain, putting together the results of several experiments, most fundamental experiments. Anyway, you get the voltage from doing this. It's right here. We know the charge came from, they'll usually have it as Millikan's oil drop experiment, where it measured the charge, but it really was J.J. Thompson way much earlier, and also Faraday, who determined the charge of the electron. So this came from another experiment, the electron constant. The mass constant came also from J.J. Thompson, one of my heroes. But he used the particle model.
Okay.
So what J.J. Thompson did was an electron gun with a magnet and deflected. And I did that experiment also, by the way, just for the fun of it. From deflecting charge in a vacuum tube with a magnet, get the charge to mass ratio. Not both, not independently. Deflection experiment of J.J. Thompson got the charge to mass ratio, and then from the oil drop experiment, they got E independently, and then putting that in, then you can get the mass. So that's how they discovered, teased out what is the mass constant of charge from a combination of those two experiments, both done by J.J. Thompson. So you get the velocity. Now we get to put the velocity in. So we figured out the wavelength. We figured out the velocity from this electron gun. Velocity is really from here.
Is it the velocity, the speed of light?
No. The velocity of charge. There's no light here. This is a charge experiment. Good question. Then the mass, that came from those other experiments that I didn't explain it completely. There's an electron gun and a magnetic field where the magnetic field goes in and out of the board with north-south. Why I drew it this way. I did that experiment with alpha rays, by the way, to deflect a charge and get the angle as a function of charge. Right here. So how is that done? He knew the voltage. Then from the did not know the charge to mass ratio. This experiment gets the charge to mass ratio. It was the Lorentz force. Force is equal to velocity, magnetic field. Force. I'm not sure if I can do all this physics just on cue like this. I haven't looked at it. I haven't prepared myself. But anyway, he did it.
Well, this was a very spontaneous.
Yeah, he did a deflection experiment, and he was able to get the charge to mass force equal to mass times acceleration. And I'm going to put an E in here instead of Q. So I think you solve this for M to E equals velocity d over acceleration. These units, something will cancel out. You'll know the magnetic field. How would you know the magnetic field? I don't remember all the details. But he was able, in a deflection experiment, just like you're very similar to the old television cathode ray tubes.
Mm-hmm.
Same way with the magnetic deflection. He was able to get the charge to mass ratio. And from that you get M, get the mass constant. People say it's the mass of the electron, and the E, they say it's the charge of the electron. You have to be careful. They're just out these numbers from the experiments. And it's not always that the particle model works. The particle model usually works. It works in these experiments. That was the history of physics, that they used the particle model and it worked for a lot of things. But then as soon as they saw electron diffraction, which was done by J.J. Thompson's son, G.P. Thompson, George Paget Thompson, did this one. Actually, he did it a different way, where he did it where it's scattered. Some G.P. Thompson did where it's scattered through at an angle, and Davison and Germer did it where it reflected. But they were both about electron diffraction about the same time. I forgot when, 1925, around there. 24. And that was really startling because here the father and son were coming up with opposite models. The father said it was the particle, the son said it was waves. I have G.P. Thompson's book, by the way. I have all their books. And so it's these experiments that had people thinking, well, what do we do with this wave? how is it that particles act like waves? So what happened? Schrodinger was grappling with it, and it looked like he was really on the right track. And by the way, Schrodinger hated quantum mechanics. Everybody says he started it.
Created. Yeah.
Created.
Yeah. No.
Anyway, you can see in his book, Dublin Lectures, which I have, and pointed out how awful it was that Max Born changed the interpretation of the wave function to a probability interpretation. Schrodinger originally had it as the density of the charge wave. Max Born changed it to probability of where the particle would be. Anyway, you have all these fundamental experiments and equations, and yeah, I was trying to justify the de Broglie equation. So the wavelength comes from electron diffraction. The velocity comes from the electron gun. The mass comes from the charge to mass ratio experiment. H came from black body Planck, which fit. It made everything fit in this experiment. This experiment justifies the de Broglie equation after they read all these things, all these numbers. And so it also fit in the photoelectric effect. So when you put the constants in, everything fit. They liked it. It was great. But it was a mix of wave interpretations and particle interpretations of these early experiments. So now I'm going to erase a bunch of stuff, sort of start over. I don't have enough room. So I agonized over this for years, to figure out what the hell's going on. And if you look at, let me write back the equations. It's do one at a time. We don't get all of these constants from one experiment. You get ratios from the experiment. You have to put the m here. In the electron diffraction experiment, you get the H to M ratio. When you read the experiment, the message of the experiment, you read the ratio.
Okay, let me put this down. I'm starting to realize what you mean. Yeah.
Yeah. And then from the photoelectric experiment, let me write down the photoelectric equation.
Sorry, the mass, it came from what experiment? Was it J.J. Thompson?
J.J. Thompson's electron gun.
Yes. J.J. Thompson electron gun. Yes, but nice.
In combination with another experiment that got the charge constant that J.J. did, which was an oil drop experiment. But amazingly, he was able to see something pretty close to the right number. And
but the charge is not here in this equation. So it was on the other.
It is. There's two ways of writing the photoelectric effect equation. you could do electron volts. Do it both ways. So the charge is there. The photoelectric equation is written both ways, this way and that way. So I'm going to rewrite it, where I'll do the E to H ratio is equal to frequency over volts. The experiment will read the frequency, will read the volts, and then you'll be able to calculate, just read from the experiment, this ratio. The message of the experiment gives you the E to H ratio. It doesn't just give you H, the way your textbooks say. They stole the E from another experiment to put it in there. Didn't tell you that, but it gives you the E to H ratio from the experiment, the message of the experiment. Also, if you look at it this way, it's H to M ratio is equal to the velocity squared over 2. And so that's what my chart is, where I show these different equations and say, well, what is the message of the experiment itself? And you see these ratios.
Yeah.
And it's been blowing my mind ever since I found this, that nobody else saw this. Absolutely nutty. That I'm finding that the message of the experiment is in the ratio, and there's another ratio. There's I think it's M to E ratio. E to M, H to M, E to H. What's the third one? E to H. E to M ratio. There's another kind of double slit experiment done by Aronov and Bohm, where they had a magnet in the middle of the double slit that used the E to M ratio. That was more modern. Incredible stuff. Of course, all of those experiments were analyzed, interpreted with wave-particle duality, where really didn't know what was waving. They thought they put the wave into a probability function. So I'm going to do a way. Let me erase some things.
There's one difference in E to H and H to M, that H Planck constant is on the other side of the ratio. But it's a ratio, even then. But
electron volts equals nice constant. Did I write it wrong?
I don't know how. Yeah, should it be on the?
Could be written either way. H is still there either way.
Yeah. Yeah, but I mean the final ratio you want to bring up there. It's on the with the mass you get the H over M, but with E you get H over H. Right. Yeah.
It's okay. Planck's constant is still in both equations. Yeah. So there's three different ratios I'm talking about. There's the E to H ratio, the H to M, the three constants. What would be M to E? And you could turn those upside down, whatever. Those are the three ratios that show up in the experiments that are anything close to wave properties. You'll always see those ratios. Now, if there are experiments that are more to do with the atom and real particles that hold themselves together, you'll see powers these ratios. That's when it really is holding itself together as a particle. So it's not about spreading waves kind of thing. So I'm picking out the equations that highlight the wave properties that have these ratios. So the trick that I did was to connect the de Broglie with the photoelectric equation, to connect, to relate these two equations. Like this is a wavelength equation, and this is a frequency equation. And you think that there would be an easy way to connect, to relate a wavelength equation to a frequency equation. Now, there is an easy way. It's that what's nu is equal to A over, what's nu here? Right. Frequency is velocity over wavelength. You can relate wavelength and frequency with any periodic phenomenon. This equation holds. It could be water waves or beats, envelopes, light waves, charge waves, anything periodic. This is going to work. So you go ahead and you say, oh, well, let's just use it. Try to relate these two. And okay, here's a wavelength. Let's just cram it in here. So on the over F. So let's just put it in there. Equal to B on the is B over F. Okay. I just substituted in for wavelength.
Mm-hmm.
So you get what? B squared over F. So what I'm trying to do is connect these two equations. And what do I have so far? I have HM is equal to V squared over F. Did I do it right? I may have screwed up. I could have easily messed up something.
Isn't this the same thing? Those both do. Oh, but there's but there's two behind. No, not exactly same.
HF over M. HF over M. See, I did do it right. All right, so when you try to do that simple velocity equals frequency times wavelength equation, you're a factor of 2 off. It's just this factor of 2 that's wrong. Now, nobody knew how to correct. I corrected this. I knew how to correct this factor of 2. And it has to do with difference frequency. I'm going to show you. I think I'm okay now. I did not make a mistake. So this is how I developed the theory. I was trying to connect a wavelength equation to a frequency equation at the very beginning of modern physics of the electron. So, oh yeah, factor of 2 off. Well, I went to the spectrum of the hydrogen atom, where Balmer, I forgot what year it was, early 1800s, he found that the frequency of light was a difference between 2 terms. There were 2 frequency terms, and it was like fractions. And so I forgot how to write it. But there were 2 terms, and there was a separation. There was a difference between them, and so this was done by Balmer, Rydberg, and Bohr. If you look up the Bohr equation of the hydrogen atom, you'll find that it's about a difference frequency in I call it a frequency of the psi wave, Schrodinger's psi wave. They call it something else. But there are 2 terms. This whole evolution of the spectrum of hydrogen, that there's 2 terms in it. And from that's all you need to know in the equation. That it's about a difference frequency. That there are difference frequencies going on in the hydrogen atom. You can see it in the structure of the equation. You don't even need to see what's inside of it other than it's about difference frequency. And that gives you the frequency of the light that comes out. So you can look up the equation of these people who did that. And what I'm saying, if it's about difference frequencies, you can model what's going on inside there like a beat. Beats are difference frequencies. Forces the idea that what's going on inside of the atom, you can see from the spectrum that fits the spectrum, it will predict the spectrum accurately of hydrogen. And I think some other isotope of hydrogen. But hydrogen tells us that what's going on inside is about difference frequency. And I'm saying that's about what the electron is. These really are about what electrons are doing. You move charge and you get light. So it's really obvious that this is the structure. To me, it was obvious that the structure of the electron is about beats. This is the identity of charge. So I was able to look back at these simple equations and experiments to see, well, obvious, and it's very similar to pictures in the books. They'll have beats going in circles. Like the Broglie did something very similar to this. He didn't quite get it right. It was close, where there were standing waves, and you'll also see it when you solve Schrodinger's equation for like particle in a box and all these samples they give for finding the solutions of Schrodinger's equation. You'll be able to, you're forced to put together standing waves in many cases. So it all fits. That standing waves is another way of seeing going on here. Either a standing wave is a combination of two waves going in opposite directions that are adding up to still have an envelope. The electron is about envelopes. So you can pretty much figure that, well, I figured that the inner wave is Schrodinger's psi wave. And Schrodinger talked about this. It's in Schrodinger's first paper that he said the electron was about deep difference tones. I can pull it out if you want, but it's these quotes that I'm giving. I'm talking from references of the works of many great people, not just bringing things out of nowhere. Schrodinger he just about had it. And from this discussion of difference frequencies in charge, that's how he went and did his equation that everybody loves that's used in quantum mechanics. Started from this, from difference frequency, amazingly. Mm-hmm. But I'm looking at it in a simpler way. I'm not beating Schrodinger's equation. Turns out that all of the solutions of Schrodinger's equation are just sines and cosines and exponential decays, combinations of those. And that's all we did. In our quantum mechanics class, we said, oh, well, let's just try combinations of those kinds of equations, sines, cosines, exponential. And then we put them into Schrodinger's equation, and it worked. Well, okay, that means we know that we can use simple sines and cosines and exponentials. That's pretty much what Schrodinger's equation is about. Mm. But let me go back to this. This was really key. I'm saying this is a special wavelength. This is the wavelength of the beat. You use the wavelength of the beat, then you solve that factor of 2 error. I solved the factor of 2 error by putting light, the wavelength of light here. The way light fits charge. This is my theory. The way light fits charge, that it fits around beats. Wavelength of the light fits charge like this. And then I get to write down my own equation. Everybody else's equation I took. But my equation is that I convert it into frequency, and I always get confused when I do this. So it's that the frequency of the light is equal to 2 times frequency of the beat. I have to look at this. Do I have the 2 in the right way or what? Twice the frequency of the beat, frequency of the light. Now, so twice the frequency of the light. Here's the frequency of the light times the frequency of the light. Then you take this and you put it in for the frequency of the light. In the photoelectric equation. No, wait. Put it in here. Yeah. Let's see if I can do it.
Mm-hmm.
Um, so I'm going to rewrite this. So I'll get, yeah, it looks right. So mp squared over 2 equal to that. Like, did it. That was the big breakthrough. Just relate the Broglie equation to the photoelectric equation. Get it straight without this, without all kind. I've seen other people try to do this in books, and they go through all kinds of horrible contortions. Just not necessary. They didn't even connect the two. They tried to derive one or the other. Anyway, it looks like I'm the only one to connect those two equations with this. Pretty sure I am. With this simple model, how light gets charged and the hydrogen atom. But so that's the beginning. So I'm not finished. At least I know how to use waves and charges and wavelengths and stuff. So you use this same model to derive the Compton effect. That was the next thing I did.
Mm-hmm.
But the same structure used for the derivation of the Compton effect. And then, by some miracle, I kept thinking about this, realized that to do the ratio trick. And then look at many other experiments, like the Stern-Gerlach experiment, and see, oh, there's no problem. You do not need to hold electrons. The earliest original problem was to use the particle model of the electron and to think it really was particles. But no, saying it was just a model that gave us much mileage, did great, but it's just a model. And then there's wave models that are irreconcilable with the particle model. And that's really important. There's no way to put together waves to explain particle effects. You have, and the opposite is true too. There's no way of putting together a bunch of particles to explain, like, the double slit experiment. People try to do that all the time, and it's just doesn't work. And if you do anything more complicated than a double slit, you're just lost. to explain interference and diffraction, all kinds of polarizations and properties of waves, it's just laughable to try to do it out of a pile of particles. And that's mostly because this collapse of the wave function problem. If you, many of these explanations will say, all right, let's just slow down the rate of the particles and just make them one at a time. They'll say, oh, well, we'll have a particle going through, it'll go here and here, build up one at a time. So this is the way they'll do it on YouTube videos. They'll try to explain the paradox. Do silly things like close one slit and everything.
You get a paradox if you use the particles.
That's right. If you use particles, you do not get an interference pattern. You only get an interference pattern if you use waves. Because whatever's going through has to go through all the paths to get the wave distribution, the interference pattern. So that's part of the paradox. But the paradox is even more horrible than that. That's just the beginning of the paradox. The real paradox is when you do it, instead of two paths like this, you do it in the beam split coincidence experiment, where it looks like when it shows up in one place, it eliminates the other place. And that's the real paradox of wave-particle duality. When it shows up in one place, because they'll think of it that way, they'll analyze the experiments that way, because to them, it's a particle guided by a probability. All the mathematics, the way people have looked at these experiments, that particle attribute is superior, that it's really a particle guided by a non-physical wave function, according to them, and so that when it shows up one place on the screen, it won't show up someplace else because it's a particle. That's the mathematics of quantum mechanics, and that's how they think about all these experiments. So when they go to the beam split coincidence experiment that we're doing, and I'll just draw it like a beam splitter. There's a detector. And they see, oh, it goes to one place and not the other. That's a pulse. They'll say, that's really nice. It fits quantum mechanics. And they'll get a band of noise on the delta T graph. 0. Oh, it hits this time and this time and this. No peak. 0 nanoseconds. So they tried that several times and they keep doing it. And there's several experiments they keep doing wrong. So that's why we're doing this experiment. To see through the illusion of quantum mechanics. It's a very difficult illusion to pass. It usually works. Everything seems to fit, except you need to give up making sense of the world. You need to give up that there's some way the wave will make sense to collapse. The wave function in the analyses of quantum mechanics, that wave, it goes everywhere, the whole universe. And then, and you'll see it in the writings of, the earliest writing I found was Heisenberg, his book. I have it right in front of me, where it talks about collapse of the wave function. So they understand it's kind of nutty way back there in the 20s and 30s. They knew it was nutty, but they just use it anyway. The wave function collapse. That it goes everywhere and then just goes away. Well, since no one has been able to show a distinction between some alternative to quantum mechanics, they think the world really is that nutty. And I'm growing up seeing this, and I'm just not going to let the world go on being nutty while I'm alive. And that's why I put all that energy into figuring this out. It was too nutty. They're thinking the world really is inherently paradoxical. They know. Just have not figured out the solution to a difficult problem. It's not a paradox, it's a problem. It's been a problem so long, it's been called the wave-particle duality paradox. For good reason. It's been a problem for a long time. Anyway, see some of where I'm coming from. That the idea of wave-particle duality and the photoelectric effect and the photon, it was argued against by many great people, and I stand with them. I'm standing with, even with Einstein, when in this 1935 paper. I'm standing with Schrodinger, Sommerfeld, Debye, Lorentz. Hendrik Antoon Lorentz wrote a whole paper saying photons will not do. He wrote a whole thing about the wave collapse and waves going everywhere, and he said, this is just ridiculous. They knew it was nutty, but they ignored those people. Said, other scientists tried to say, well, the experiments show it that way. Just go away about your objections. That's what's happened in the history of physics.
Isn't it ironic that if you think Einstein, that he was against this spookiness in quantum mechanics and all this EPR paper and all those, but on the other hand, he was the one who began this whole dilemma with the particle like photons. So it kind of starts. That it starts there and it gets him to the trouble.
That's right.
Yeah,
that's right.
And from your point, Einstein is correct that quantum mechanics can't work this way. There's something wrong with it, but he don't realize that it started from his creation.
Oh, he knew. Yeah, he knew it started that way. He was agonizing over quantum mechanics the whole time he was working on gravity. I see all various accounts. He was still trying to figure out this problem. It's always a problem. His saving grace is that in the 1905 paper, he called the model, he called it heuristic. The title of his paper is A Heuristic Understanding of the Interaction Between Light and Charge. That's a good way to put it. But people took it much stronger, and he even used the particle model of the photon. Well, let me be more clear about that. It was clarified really well in Niels Bohr's book, where in Niels Bohr's book, he paraphrased, I told you this before, Bohr paraphrased Einstein to explain what is a photon. Well, Einstein actually had it right in this sense, that the photon is just a model. It's just how to look at experiments. But and the model of I can just open up the book and read it to you again. If a semi-reflecting mirror is placed in the way of a photon, leaving two possibilities for its direction or propagation, the photon may either be recorded on one and only one of two photographic plates situated at great distances in the two directions of question in question. Or else, we may, by replacing the plates by mirrors, observe effects exhibiting an interference between reflected wave trains. So, finding the model of the photon in terms of two experiments that give contradictory results. That's right. That's what the photon is. It's a contradiction from the very start. So if people say that a photon is a particle of light, they're missing the point altogether. People try to put light where there's some blob, a fuzzy ball going across space, saying that's a photon. They've missed the point, because that kind of particle-like picture of a photon will not fit this one-way. It will not explain wave properties. It will not explain interference. As soon as you hold together some wave packet, as soon as you try to put the photon in a wave packet that holds itself together, going across space, you'll not be able to explain an interference pattern. It'll go through one hole or the other. It won't hold itself together. Look, what's the definition of a particle? That's the best way to start. A particle will hold itself together, and a wave is just the opposite. The wave does not hold itself together. It spreads everywhere. Just start with what's a reasonable definition for a wave and a particle. Now, I'm talking classical waves and classical particles. But quantum mechanics people will do this doublespeak by saying a quantum mechanical particle will have wave properties by the probability interpretation. So
it's just a
right,
collapsed wave.
That's right. You make it collapse. So Einstein's definition of the photon is the same thing as the experiment we're doing. The first half of his sentence. The second half of his sentence to say, let's recombine these two beams put it together, and you'll see an interference pattern. If it was to go one way or the other, it would not make an interference pattern. That's the paradox. But yet, that's the definition of a photon. And that's the beginning of all of quantum mechanics, where it starts you out with this contradiction. Starts with a contradiction with any way of putting it together in space and time. Just a recipe. Quantum mechanics is a recipe, and then there's this argument over, well, does it fit? Does it work? And they'll say, oh, yeah, all the experiments show that it works. Well, they did not know how to put the experiment together so that this experiment that we're doing fails. They did not know how to do that. They never had a decent model to understand how would you put together the experiment to show that it does not go one way or the other in a beam splitter. And it's hard to change gears, to think differently, because the whole time you grew up thinking, well, energy conservation in terms of particles. You'll think, oh, well, energy is proportional to frequency and all that. That's true. Energy is proportional. Well, it usually shows up that way. If you think this way, then you'll say it has to go one way or the other because we're reading whole pulses. It has to go one way or the other, this way or that way. Otherwise, you'd be violating this equation.
Mm.
And there's a way to see that this equation is still true. But you could get one way or the other. And that's what's inspired by Planck's second theory, that H is a maximum. Make H understood as a maximum that loads up. Then you get to not see everything in terms of particles going up there. So the trick that I did with Planck's second theory is I just expanded it. Instead of just H as a maximum, do the same thing with E and M. To make those also as maximum, and then be able to put it in ratios. So what I'm doing.
Can you put it some other way? What does it mean to be a maximum here?
Yeah.
Like H as a maximum.
Right. Yeah. The value of Planck's constant is about a maximum of action. So it's an action constant. What's action? Action is whatever you do to solve this equation to have the units work. It's energy divided by frequency, which is energy times time. So I'm saying action is thresholded, and at the threshold value is H. And the same way with E and M. But you will not understand that those are just threshold values, because when you look in the experiments, you don't see just individual E and M. you see the ratio. So if there's less, look at the E to M ratio. I'm saying E is about a maximum of charge. Well, let's say you have an E over 2 of charge and an M over 2 of mass, some sub-threshold value, less quantized. Turns out these parameters track each other so that they'll always have the same fraction. The 2's cancel out. You won't know it. That's the illusion of quantum mechanics.
But you suggest that in reality they can be in maximum or they can be in some value between their 0 and max.
Right.
Yeah.
But it's that the parameters, what do you call them? Charge and mass. The ratios are conserved. The real constants, well, there is such a thing as the charge constant. It's the threshold. But the ratio is also a constant. The ratios are conserved. The experiment of J.J. Thompson with the electron gun showed that the charge to mass ratio is what's conserved. He discovered that. So then you get to say, well, what happened with the oil drop experiment? Why did that show up as quantized charge? Well, it's an ensemble effect. You have a whole bunch of this stuff going on, pulls itself together. Because it's about forces, pulls itself towards the threshold. So when you get nuclear wave functions together, which will work the same way with much finer beats, that's what made this ensemble effect that allowed us to see the charge constant. Now, there are other ways to decipher the charge constant. There's a Faraday method and there's a shot noise method. There are a few other methods, but they're all ensembles. And the main point is when you use the charge in free space, it's a big leap of faith to say that it's going across space packaged that way as a particle. You know why? I'll tell you why. You should know why. Because charge diffracts. It is not packaged that way. So you're entering the paradox. Well, that's been the big mistake. They kept using charge as quantized. And when they looked at the photoelectric effect, they saw, oh, a whole electron got thrown off. How do you get that? Well, it must have been a photon, so they say. That's the history of physics. Modern physics.
Yeah. What explains then that in these most of these cases in beam split experiments, you will get you kind of have this maximum value in H and M and those because they work and they need to have this maximum, I suppose. But what is the reason that in most of cases it's maximum, but then in these few other cases it's not? It's something between. Is it related to the just to the electromagnetic magnetic wave spectrum they use in the experiments?
So these are mostly experiments on charge, about charge, the electron model. What I really have is a theory, a hypothesis of the electron, the model of the electron. It's really what my theory is. There's a thing about saying the word theory. Anyway, people do it all the time. It's really about charge. And I was trying to explain in the experiments that show wave effects, you'll see ratios of these constants. And you could use the whole value of the constant. But since it's in a ratio, you could not tell if you have less really there. Because it's in a ratio, it's the ratio that's conserved. That's nature's ratio trick. Let me redraw. Let's say you have an electron that's emitted. I'm going to use my model. And it's like a puff of charge that will then spread. And so it's sort of going out this way, emitting charge. However you want to distribute this piece of charge. You can take a piece of it. Just take a cubic volume of it. And say, well, how much charge is going to be there? First, take how much charge is going to be in the whole thing. And E, the whole E. How much mass? There's going to be a mass constant associated with it. The whole M. Here's this charge wave that's been emitted. The whole thing is E and M, all big letters, the threshold values. And you just take a little piece of it. Just take a chunk of it. Well, there's going to be a less E. It'll be like a tenth of an E, or a hundredth of it, or a hundredth of an M, some fraction. And you could put H in there too, of a fraction of it. I'm saying if you take any fractions of this charge wave, you'll just see the whole fraction. You won't see. You won't see that it's a fraction. You won't see fractions of E or fractions of M, because you're reading a fraction of E to M together.
Mm-hmm.
If it's E over 100 and M over 100 in here, the hundreds cancel out. And so you do that little trick with every experiment, and you find a whole different way of looking at the world. And I find that it always works.
So why in our case is when we do this experiment with the gamma rays and so with certain sources, isotopes and scintillators, why we have different values there, not the maximum? If in the most cases we have the maximums and they cancel out and we can't see the illusion, but in our case we can. How does this whole experiment kind of relate to this exact point here? Am I correct if I say that they don't? Yeah, so they don't cancel out in these special cases.
Well, No, it does cancel out. The preloaded states, the way kinetic energy in charge loads up, is to understand how a loading could work uses the ratio trick. The loading is about the ratio trick. But then when it reaches a threshold value, when the kinetic energy gets all the way up, it shows itself, then we see what it looks like a whole electron being emitted in a photoelectric effect in the scintillator.
Yes, of course. So at that point, yes, yeah.
So every time you see a click, it's about reaching the threshold. So I set it up so that we can take advantage of the shock wave of electromagnetic energy. So a gamma is like a shock wave, and it only happens in near field when you try to do this, where it goes one way or the other. And then here's something that's partially loaded. I'll draw it with little cups or whatever. So here it's going to be partially loaded, and here it'll be partially loaded. Give it a shock wave, trick it into both filling up and spilling at the same time. And you'll only see that with high photo, because this threshold effect is about the photoelectric effect. The unquantum effect is the photoelectric effect. They're all the that's what the unquantum effect is. We're taking advantage of the high photoelectric effect efficiency to where it all fills up at once and clicks. Except if you think it's a particle that goes one way or the other, it should not make the other one click. If you understand it can load up into a threshold, then your mind can attempt to understand how it could be. Well, it's a good thing to try to understand that, because the alternative is how it could not be. How is it that waves go everywhere and then collapse? So, yeah, the threshold effect right there before the detector goes click. And the fractions of e to m are down here, the fractions of it. When it reaches here, yeah, it's going to be a whole e, a whole m, whatever. You'll see the results as if you were interpreting it quantized. The threshold idea embraces quantum effects. But the threshold idea does not eliminate the preloaded state, whereas the quantum mechanics idea does. Quantum mechanics eliminates this idea of a preloaded state. They say so. They think they know so. They know, but they're wrong. I show them wrong.
So
they better be wrong, otherwise the world would be pretty crazy.
and that's not new.
But that's so say-it-true. That's just me talking, but that's me.
If you go back to the situation when this unquantum effect is not visible, so it would mean that we kind of are forced to interpret that they are particles, and also that those maximum values, those thresholds, they are always triggered by the maximum. So is this some correct way to explain?
Conventional physicists do not talk or think about these thresholds. They use the particle probability model. They don't think of it loading up at all.
Oh yeah, but when we use different scintillators or different gamma rays from the higher energy, so we can't produce the effect with every combination, just with these few. So what happens on those cases when we don't see the effects?
Yeah. Right. Why does it show up as random on the time distribution? Well, for one thing, we know the Compton effect dominates. Yeah, well, that's a good question. How is it that the loading is suppressed so strongly when the Compton effect dominates?
Yes, it would have to be related to that, because we will see this when the photoelectric effect is strong and dominates. So when it's not strong, there is Compton or pair production or something like that.
Right.
And for some reason, it doesn't. It gets random at that point. No piling.
That's right. That's right. Yeah.
But it requires a little bit like explanation how it's related to the threshold at that point.
Well, it fills up readily. It fills up very quickly, readily, when you go to higher frequencies. So that's something to be sorted out. The reasoning and more experiment to see when the unquantum effect works and does not work. Yeah. I don't have all the answers. I just went so far. I was able to see a good deal of when it does not work. But there's surely going to be more to do. I better not try to guess. I can guess a few things. I'll end up being wrong and blundering around. I better not try to do it.
Yeah.
But let me think for next time to get a good answer.
Yeah. But this was really good starting point for me to get into the theory. Of course, you have told this quite many times, but problem was that I didn't have even a right image of the experiment. So now I think I'm ready with that, and I probably can digit something and understand. I think I got a quite good idea now. It's good to continue from this.
Well, thank you. I feel pretty good about you, Marko.
And to me, after all, it kind of feels consistent when you explain all the starting points and all those things, they connect up, and I can kind of realize what do you mean there. But of course, I don't have these models that they have in the school, so I can't compare these to anything. But for me, it's quite convincing and coherent. All this talk about the ratios and so on, they are in some other associations, they are quite familiar concepts to me. I used to think that everything is what we see and sense in the world. We get it via ratios, like the lengths and the time and differences, masses. They are related to other lengths and masses and so on. So it's a familiar concept to me. Nothing strange.
Good. Good, that's right. Most of chemistry is done with ratios.
Yeah. Yeah. Thanks. And this is on the recording. If you want to send this to me, the link, I can recap and go this through again. And
I will.
Yeah. So we can continue the discussion from this. I also sent you a couple of links. There was one link. Let me see. That was related to single photon counting. This was this publication that was about the single photon counting. And then I also sent thanks again for the comments, all the comments you put on my document. There were like more than 50 comments, and it's really huge help to go through these again, and I managed to even make the changes to most of those, except the essay. I need to figure out a little bit more and think about the essay, because it's like a free thinking thing from me. But yeah, the first part, it's really good now, I think. And I sent you also kind of a feedback, like I made this change and I made it this way, and I have a few questions, and the references to the books of Planck, they are in the document. So if you want to go through those, so you can see something there.
Okay.
But don't take any pressure. You have done so much with these, so there's no really any time limit in this. I just want to go through all things in this way to really understand the experiment and also the theory now.
Good. Keep up the good work, Marko.
Yeah, and you too. Have a nice day there. Let's see our next session then. Let's email and do that with these conversation in the emails and pick up the session. By the way, after a month, I will have a 1 month summer vacation when I'm traveling here in Finland a little bit. So at that point, we might have some break, but until that, it's studying all the time.
Studying?
Studying, doing studies.
Good. Keep up the good work, Marko. Very nice.
Yeah.
All right, I'll let you go.
Yes. Yeah, thank you. Thank you.
Thank you,
Have a nice
Marko.
day.
Bye-bye.
Bye-bye.